Hey everyone, it's Zach, and today we're talking about capacitors. So enjoy, and don't forget to like, subscribe, and click on the notification button for more electronics videos. Also, watch out for sharks.
What is a definition of a capacitor? A capacitor is an electronic device that stores charge in a circuit. However, capacitors operate in a way that is more nuanced than as described in the definition. Therefore, to understand this nuance, we will go through the shark tank analogy. A capacitor is like a storage tank, but for electricity. When we open the valve and let current that is represented by water flow into the tank will store a good portion of the water, but the water will still flow from the pipe out of the tank. When the valve shuts, water will still flow or discharge from the tank until it is empty. This analogy provides a broad, non-technical overview on how capacitor storage and discharge works. The non-technical explanation will enable you to understand how capacitors work from a technical electronics perspective. A capacitor is made up of two conductive plates with an insulating material or dielectric sandwiched between them. When the capacitor is not connected to a voltage source, each plate has an even amount of charge. However, as soon as the capacitor is exposed to a voltage, the dielectric becomes polarized, causing the electrons to want to move. Since the dielectric is an insulator, current, which is the flow of electrons, is unable to go through it. So what happens? Electrons will flow from the voltage source to the negative plate, increasing the negative charge at that plate, while electrons will leave the positive plate, isolated by the dielectric, decreasing the amount of negative charge at that plate, causing the plate to become more positive. This will happen until there is a potential difference that equals the value of a voltage source. In other words, through this process, the capacitor will charge to almost the same voltage value as the voltage source. When the voltage source is turned off or removed, the capacitor will discharge until there is an even amount of charge on each plate. Capacitors are rated in terms of capacitance and voltage. Capacitance is the ability of the capacitor to store electric charge and is measured in farads. However, the farad is a very large unit of measurement. Therefore, most capacitors that you will see in circuits are measured in terms of picofarads or microfarads. A capacitor's voltage rating determines how much voltage a capacitor can handle. If the voltage of the circuit exceeds the capacitor's voltage rating, the capacitor will blow or be destroyed. When selecting a capacitor, you also need to know about capacitor types and their advantages and disadvantages. There are two main capacitor types, electrolytic and ceramic. Electrolytic capacitors are polarized, meaning that the positive side of the capacitor must be exposed to the positive side of a voltage in order to work. If the negative side of the capacitor is exposed to the positive side of a voltage, the capacitor will blow and be destroyed. However, the advantages to electrolytic capacitors are that they have relatively large values of capacitance for their physical size. This makes them ideal for circuits where limited space is available. They are also rated to handle large voltages. Ceramic capacitors, while they can handle large voltages as well, are generally restricted by their size because their plates are flat instead of rolled up into a tube. Practically, this means that a ceramic capacitor with the same capacitance rating as an electrolytic will be far larger. The ceramic capacitor, however, has the advantage of being non-polarized. This means that it doesn't matter which end of the capacitor faces the positive side of a voltage. This enables the ceramic capacitor to have more versatility in circuits than the electrolytic type. Before moving on to capacitor applications, I'd like to make the comment that less capacitance isn't necessarily a bad thing. In some applications, it may be ideal for the capacitor to have a smaller capacitance rating. such as in timing circuits discussed later in this video and filtering circuits that will be discussed in a future video. Now on to capacitor applications. The first major way a capacitor can be used is in a full-wave rectifier circuit that converts AC voltage into DC voltage. In the United States, voltage from the power company is delivered in AC. However, many devices in your house, such as your cell phone charger and your TV, use this type of circuit to convert AC voltage into usable DC voltage. The transformer takes the high AC voltage and reduces it to a voltage level that can be used in DC circuits, usually around 12 volts. Then the diodes take the AC sine wave and ensure only positive voltage enters the circuit. The capacitor will be charged by the current. This is vital to keeping the DC voltage at its required value. The capacitor, once charged, will decrease when the voltage from the diodes decrease. This discharge will keep the DC voltage close enough to its required value to be used by devices that require consistent DC voltage to operate. Capacitors can be used to manipulate the timing in circuits. Let me explain. Capacitors by themselves charge and discharge almost instantaneously. However, the engineer can control the rate that the capacitor charges by putting it in series with a resistor. The resistor will slow the flow of electrons. By doing this, the resistor will slow the charging and discharging of the capacitor. The exact rate of charge is determined by the exponential equation charge voltage at a certain time is equal to the starting voltage times parentheses 1 minus e to the negative time divided by resistance times capacitance, end parenthesis. The exact rate of discharge is determined by another exponential equation. Discharge voltage at a certain time is equal to the starting voltage times e to the negative time divided by resistance times capacitance. Based on these equations, the rate that the capacitor will charge is determined by the resistance times capacitance value. This means that the capacitor will take longer to charge or discharge when the capacitor has a high capacitance or the resistor has a high resistance, and the capacitor will charge or discharge quickly if the reverse is true. Capacitance times resistance equals time in seconds. Let's do a quick example. A capacitor rated for 1 microfarad times a resistor rated for 1 kiloohm equals 0.001 seconds or 1 millisecond. This value is called the time constant. The time constant is important in analyzing the charging and discharging of the circuit. When t equals the time constant R times C, the capacitor will have charged or discharged about 2/3, or to be more precise, 63.2% of the way. When t equals 5 times the time constant, the capacitor is considered to be fully charged or discharged. By knowing these principles, you can manipulate the timing of many circuits to meet the requirements of your design. As discussed earlier, the dielectric in the capacitor blocks current from going through the capacitor. That is only partially true. It blocks DC current while allowing AC current through the circuit. This is a very useful principle about capacitors to know because it can be applied in circuits. For example, you have a circuit that takes a sound signal from a microphone and amplifies it. The microphone takes the sound signal and converts it to an AC signal. Then once the signal is amplified via an op-amp, it needs to go to the speaker to be broadcast. However, since it's an op-amp, it produces DC voltage along with the AC signal. This DC voltage will cause an unclear sound to come out of the speaker. To mitigate this, the capacitor will block the DC voltage, allowing the AC signal to reach the speaker without being impeded. The last capacitor application I would like to discuss is when it's used as a bypass capacitor. Capacitors block DC voltage, attenuate low-frequency AC voltage, and easily allow high-frequency AC voltage through. The equations explaining why a capacitor operates like this will be discussed in a future video about filtering. However, Knowing this principle will be enough to understand how bypass capacitors work. A bypass capacitor diverts high frequencies that can damage electronic components to ground. An example of this is in the following circuit where an integrated circuit, or IC, is connected to a battery. However, the battery does not provide pure DC voltage. Rather, it provides DC voltage with unwanted AC signals. Usually, these minor AC signals don't affect the operation of a circuit. However, they will damage sensitive components such as ICs. To mitigate this, the bypass capacitor will divert these AC signals to ground, thereby protecting the IC. To summarize, we talked about how capacitors work, their types, and some of their numerous applications. Hey everyone, I hope you enjoyed this video, and don't forget to like, subscribe, and click on the notification button for more electronics videos.